Hi everyone, so today we're going to be taking a look at the last banana activity. So suppose that you're on a desert island playing dice with the castaway. The winner's prize will be the last banana on the island, so the stakes are high because you are hungry. Here are the rules of the game. Each player will roll a die. If the largest value shown is a 1, 2, 3, or 4, then player A wins. If the largest value shown is a 5 or 6, then player B will win. So keep in mind that even if player A doesn't roll the 1, 2, 3, or 4, but say player B does and it's the highest value, player A is still going to get the point for that round. So who has the advantage in this game? Player A, player B, or neither? Make your best guess and explain your choice. So think about this in your head for a moment. Who's going to win? Who has the better chances of winning this game? Player A, player B, or neither? So now, on to the next part. It says get a partner and play this game. Play the game 20 times and record the winner of each game by the tally table below. Well, I cannot play with you since we are virtual and this is a video, but instead what we have is this lovely website called random.org where we have 2 dice. And I'm going to say the one, well, it doesn't matter. So we have player A is going to win if we roll a, oops, different screens. If we roll a 1, 2, 3, or 4, then player A is going to win, and player B wins if we roll a 5 or 6. So here we go. We are going to roll our dice. Alrighty, so we have a 5 listed, which means player B wins, because 5 is the highest. We're going to roll again. 6 is the highest, which means player B wins again. We have 2 2s here. So for this one, player A is going to win. We have 2 6s. That means player B wins. We have a 4 and a 2, which means player A wins. A 3 and a 4, so that's player A again. A 6 and a 5, that would be player B. Oops. That was a 5 and a 4, so that's player B. 1, 2, 3, 4, 5. And then this one is player A. Player A wins again because 4 is the highest. And remember, player A wins. If a 1, 2, 3, or 4 is the largest value, then player A wins. So pretty much if you roll a 1, 2, 3, or 4, then player A wins. We have a 1 and a 6, so that would be player B. Player B wins again. Player B. That would be player A. Oops, that was player B, and this is player A. Player A. Player B, let's see where we at. 2 left. That would be player B. And player B. Is that all right? 5, 10, 15, and that would be 20. Okay, so we rolled 20 times. So if we look at our proportion of wins, out of the total of 20, we have, let's see here, 5, 6, 7, 8. That would be 8 out of 20. Or in other words, that would be 4 out of 10, so that would be 0.4. And player B is 12 out of 20, which is 0.6. So 60% of the time player B won, 40% of the time player A won. That may or may not go along with what maybe your initial thoughts were in question 1. So in question 3, the process of imitating chance behavior is called a simulation. So what we did is we simulated this game which I did through the virtual dice, and if we were in class, I would have actually had you play the game with those in the room. The long run proportion of times an event happens is called the probability of that event. Simulations are powerful tools that can be used to estimate complex probabilities. Based on the simulation by you and your partner, what is your estimate of the probability that player A wins or that player B wins? So what do you think? Based upon your results, how do you think you could make a prediction for the probability of player A winning in the future and the probability of player B winning? You might be sitting there thinking, well, right now, from the information we have, it's a 40% chance for player A and a 60% chance for player B. But maybe you would be thinking, well, 20 just doesn't seem like a big enough number to be able to make that prediction into the future because we haven't done this simulation enough times. And I would say that you're right. So if we were doing this as a class, we would collect the data as a whole group, and you would begin noticing that their numbers are similar, likely, to the ones that we got in our simulation on the last page. So as it turns out, what we were doing is what's called a probability based on past events, but we can actually find the exact theoretical probability because we can look at all the ways that the dice match up. So we've listed all the possible outcomes of rolling 2 dice. This list of all possible outcomes is what's called the sample space. So we have 36 different ways the 2 6-sided number cubes can match up. We're going to use the sample space below to calculate the theoretical probability that each player wins. So each of these are going to be out of 36. Because there's a total of 36 options. Now remember, player A wins if there's a 1, 2, 3, or 4 is the highest, and player B will win if 5 or 6 is the highest. So I'm just going to go through and highlight where 1, 2, 3, and 4 are the highest. And that's it. Then, where 5 and 6 are the highest, are all the ones that are left, which is right there. So, if we count this up, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And then if we count the other ones, so here we have 2, 4, 6, 8, 10, 12, 13, 14, 16, and we have 18 here. So if we go through and actually divide these, 16 divided by 36, we get this to be 0.44. Oh, I did not count right. Let's try that again. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Nope, that's definitely 16. This has to be 20 then, so what did I miss? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Yeah, no, it is 20. I miscounted. Sorry, guys. I know that was some awkward troubleshooting on my end. But let's keep going. So we have 20 divided by 36, which gives us a number that's much more sensible. 0.56. Now, I know technically these decimals are repeating, but we're going to round them slightly. So we have 0.44 and 0.56. So how does this compare with the estimate you made in number 3? Well, in number 3, we did pretty good with our simulation we did virtually, which was 40% and 60%. Now, what if the game was based on multiplying the 2 dice together? So if the product is odd, the odd person wins, and vice versa for evens. Complete the table to create the sample space of all possible products that we could get. So here, it's not which one is the highest, but instead it's if we multiplied them together. So to fill out this table, we're going to create the sample space of all products. So 1 times 1 is 1. Then we get 2, 3, 4, 5, 6. Now I'm going to take the number 2 at the top of this column and multiply it by all the numbers in the rows. Then I'm going to multiply it by 3. And then 4. And then 5. And 6. All right. So now, if we look at the probabilities, use the table to find the probability of the following. The probability that odds wins. So we need to look at, out of all 36 different products, what's the probability that they'll be odd? So we're going to look at it as out of 36, and then the numbers that are odd. There's 1, 2, 3, 4, 5, 6, 7, 8, 9. Got 9. So 9 out of 36, which is 0.25. Then the probability that evens wins. Well, you know that's just the complement, right? Because if it's not odd, then that means it's even. So if 9 out of the 36 is odd, then that means 27 out of the 36 must be even, which would be 75%. Probability of it being a 4 or a 5. So here we're looking at out of the 36, which ones are a 4 or a 5. So we got 1, 2, 3, where it is a 4 or a 5. Oops, 5, 6. And I think that covers it. So we got 5 there. So 5 out of 36, which is about 0.14. And then the next one says, what's the probability it's a number besides 6? So any number other than 6. So for that one, it would be like looking at 1 minus the probability that it is a 6, using what's called the complement rule, right? 1 minus the probability that that does happen will give you the probability that it does not happen. So if we look here, a 6 happens 1, 2, 3 times, 4 times. Okay, so we're going to do 1 minus 4 out of 36, which will give us 32 out of 36. Then it says, what's the probability of it giving us a number from 1 to 36? That's 100%, right? So let me triple check that with my key. But so there's a couple of things I introduced in here, which one is the complement. If you've not filled in the notes for that for Chapter 5, then please make sure that you do, which I think that is in 5. Yes, that is in 5.2, so it's after the last banana. So complement is just looking at the probability of an event not happening, and you can find that by doing 1 minus the probability that the event does happen. After this, you should be good to fill out the rest of the 5.2 notes. So you'll notice that this last banana activity is, I think, a printed activity sheet, but then I also kind of have it up here at the top, so you can disregard this. And then what you'll need to fill in for 5.2 notes would be starting here with some of the general rules of probabilities, and then I give you some practice problems on the back here for 5.2. But that wraps up the last banana. There's the 5-2 day 2, which is just going over more probability rules and things of that nature. So hopefully this is beginning to look a little bit like some of the probability that you did back in Algebra 2. But other than that, this is the last banana, and we're all done. See ya!